Hello, Surajit sir.
Hello. Hello.
Yeah, actually, sorry to interrupt. Actually, regarding the pointer, like when you are in the full screen mode, then when you right click, the pointer should come. It won't come when you are in the normal.
Oh,
Are
okay,
you in
okay.
the?
Maybe Shurajita, you can check
Yeah,
once.
you have to go to full screen mode first, and then you have to right click.
Okay, okay. Thanks. Maybe he's not around. Oh
Sorry,
yeah.
Otin.
So
Yeah.
you just make it full screen mode. Go to full screen mode,
Okay.
and then right click. The pointer should come. Pointer option.
The
Yeah.
pointer options are coming. It is just that ball, point,
There is
pen,
a
those things
highlighter.
highlighted, but it will
I don't know.
highlight. I think it just highlights.
Oh, okay. Oh, okay. I don't know. Then
It's
Joy,
okay.
you can tell.
Now choose the ball pointer. Let's see.
Ball pointer.
Yeah, one laser point used to come in my case.
So I think it's the.
I saw it yesterday, but then I somehow don't
uh,
see now. But maybe I saw it for for somebody else who is doing. So it's all right.
Yeah. Surajit, your system is not that updated.
Come on, I myself am old, so how can it be?
Yeah.
Yeah, I just want to cross check if all the speakers are here.
Suraj is
Yes, Mano.
Yeah.
Slowly they will join. Don't worry.
actually, we have Atin sir. We have reminded all
Krishna.
four of them. The rest of the four we have reminded. They said they will be on time.
Okay, then it's fine. Then you
Okay.
talk to them, right? Okay,
Yeah,
thanks.
we have already talked to them, all of them. Yeah.
Okay. Okay.
Yes.
Hello.
Hello. Shivankar. Yeah. So yeah, it's okay. Thanks. You are the next speaker. So maybe
Yes.
we'll. So you're okay with the slides. So you don't need to check, right? It's okay.
I mean, we
Sorry.
can just quickly, if you want, we can just quickly check.
Yeah, it's okay. It's okay. We have to start the first talk. So it should work, right?
It should work.
Yeah.
I hope so. Okay.
So let's start. So welcome everybody. Good afternoon. So my name is Atin Pal. I'm from SNBO Center. So I'll chair the session. So today we have total 5 talks in this session. So first talk will be given by Professor Surajit Shah from IISER Bhopal. So he'll be talking on topological phase transition at will. So his title of his talk. So Professor Shah.
Otin, for introducing me, and most importantly, I would like to thank all the organizers, with special mention of Manoranjan and Otin, for giving this wonderful opportunity to me to share some of our recent results. So I'll just switch off the video so that we can start on this. Okay, so as you can see, here is the title of the talk. Otin, can you hear me?
Yeah, we can hear you.
Okay, good. Yeah. Fine. So this is the title of the talk, and it's basically based on one of our recent work, which was by Shubhodip. And so here are the people who really deserve the actual credit. So Shubhadeep is the person who did all the experiments, and Shaheb and Ankita were the biggest helping hand to him to materialize each and everything required to execute this problem. And our results that we're going to discuss today are based on single crystals grown by Ravi's group, where Mahoshi and Saurav were the people who did this growth. And I'd like to also thank the funding agencies, especially SCRB and DST and our own institute for the fundings. Now, so to start the talk, as we know since 2003, 2004 onwards, that a surge of 2D materials where people have been interested in to investigate various types of properties. And if we really now think of today where these 2D materials fit in or can be clubbed in, so there are at least these three examples or sets where we can fit them in. So one is very well known is the graphene family, where comes graphene, boron nitride, and then the other examples of this. And then there is another class, which is two-dimensional chalcogenides, which are transition metal chalcogenides mostly. And here we have huge examples of various compounds, where sulfides, selenides, tellurides, these are the commonly seen chalcogens, and the transition metals are mostly molybdenum, tungsten, and several others. Now, the oxide counterpart of the similar thing is this, where again, there are many, many examples. And now, interestingly, if you see the interest on these 2D materials is, they show a wide variety of electronic properties. So, for example, graphene is more like a metallic system, and then there are many two-dimensional materials which fall in the semiconducting category, and then boron nitride, we know it's a good insulator. And then apart from that, we also are aware of that, there are very good examples of two-dimensional materials which are superconducting in nature. And but for today, we're going to focus our talk on one specific example, which is molybdenum ditelluride. Now, though I said that the interest began in 2003 or 4 onwards, but if we really look back in the history of literature, we find that the existence of TMDCs were there way back in at least in 1923. That's what we could figure out, where Linus Pauling first showed the structure of MOS2, and then the first exfoliation was recorded in this. I mean, at least to our knowledge, this is the first exfoliation recorded in 1963 in this publication, and the first monolayer example appeared in 1986. So as we can see, these examples of TMDCs and the exfoliation and monolayer existed even in quite long back, almost like centuries back. Now there are many interests on these TMDCs, especially talking about applications. So as we can see here, just some glimpses of those various applications that one can think of, starting from medical tools or sensing, and then different types of devices that one can think of. But then apart from that, there are also some fundamental interests, and so our experiments today have most more interest in terms of the fundamental, which of course have some possible applications which one can think of or imagine. Now, as I just hit upon with the title, which was about topology or topological phases of TMDCs, especially one compound, as I just mentioned, which is MOT2, I would like to just touch briefly what are the topological phases that we are really concerned about that is relevant to our data or the discussion that we're going to have today. One is the quantum spin Hall phase. And as we know that quantum spin Hall basically is a very exotic phase that commonly is seen in two-dimensional electron systems, where the bulk of the system remains insulating, while the helical edges show the spin up or spin down conduction. There is spin up or spin down, So this is one of the interesting thing, and how it happens, as we can see, there are these are three, and of course there are some other examples of the structures that can be explored, but commonly seen structures of TMDCs is this hexagonal structure, which you can see in this lattice structure here. Then the other commonly known structure is the 1T structure, where this is basically a rhombohedral, and the another one which is 1T prime, which is basically a distortion that happens where you can see here. So this is one layer example of 1T, where there is uniform distance or separation between the transition metal element. Whereas after it undergoes a distortion, which is piles-like distortion, it shows that there are dimerization of the molybdenum atoms, and this is what gives rise to a new structure which is called the 1T prime, and this happens to be in the monoclinic phase. Now, in terms of their electronic properties, so the H and the T phases are usually semiconducting. Sorry for this spelling. And the 1T prime is semi-metallic. Now, once this distortion happens and once one takes care of the spin orbit coupling in the system, there are these exotic changes that happen in the band structure. So as you can see, so there is this conduction band and the valence band, which you can see. So the black one is basically without taking care of the spin orbit coupling in the system. And these are the conduction and the valence band. The moment one takes the spin orbit coupling in the calculation, so one sees that there is a camelback-like shape of the band. And this is where the quite interesting features come up. And you can see, so here is the band gap, and here is what is the 2 delta in the gamma point. Now, this is what is referred in this article, which changes due to this distortion from the trivial phase to this non-trivial phase, which is what the 1T prime is about, showing the quantum spin Hall phase. Now, the other phase, the topological phase, which is also interesting for our discussion today, is the wild semi-metallic phase. And that is when, now, once we take care of the spin orbit coupling, so we saw this, the band, inversion, and that when we think of preservation of the time reversal symmetry and the inversion symmetry, one basically gets the Dirac point in the system. On the other hand, if let's say one of the time reversal symmetry or the inversion symmetry is broken, so it gives rise to wild points. And that's where the other interesting phase comes up. And now there are 2 types of semi-metallic, wild semi-metallic systems one can think of. Hello?
Yeah, any issue?
No. I just heard some sounds. I was wondering. Fine.
Next.
Thank you. So now, so depending on how it overlaps with the, the Fermi level, so we have type 1 and type 2 semi-metallic systems. Now, the more important point in this is the inversion symmetry or the time reversal symmetry. So in this case, what is more important to us is the inversion symmetry, which is broken in the system that we are talking about. So as I mentioned in the beginning that we're going to discuss about MOT2, let's see what it is about. So MOT2, when we see in bulk, so it basically undergoes a very well-known structural phase transition, which is because of the inversion symmetry breaking. And that happens from the 1T prime phase, which retains the inversion symmetry, which is the high temperature phase. And at low temperature, it goes to a TD phase, which is an orthorhombic structure. And that's where the inversion symmetry is lost. And this is the X-ray diffraction data of the single crystal grown by Ravi's group. And now, if we look at the typical transport, the 4-probe transport property, the resistivity versus temperature of this system that is undergoing the structural phase transition, we see that in the high temperature phase, which is also known to show the quantum spin Hall phase, it undergoes this change in the resistivity, and then this comes out to be the wild semi-metallic phase in the TD structure. And then upon the cooling and the heating, we see that there is a clear hysteresis right about 250 or 240 K in the system. And then we recorded Raman spectrum across this temperature, the phase transition, and we could see that high temperature, which relates to the T prime phase, that is the monoclinic phase, and that has the inversion symmetry. So there we have this typical Raman spectrum where one can see, we have just label them from P1 to P9, and then there are two of these anyway. But once it goes to low temperature phase, which is the TD phase, and also happens to be the wild semi-metallic phase, there we see an additional peak coming up, which is right over here. And that's where is the signature in Raman in terms of the structural phase transition. Now one can ask actually from this transport or this Raman, how can one say that whether it is a quantum spinol phase or the wild semi-metallic phase? Of course, we are not claiming that, because that was already established by Pashupati's group and several other articles in 2018. And so we are basically taking those references and following the understanding that the high temperature phase is basically the quantum spinol phase, and structurally that is the 1T prime, or rather monoclinic. And as we go to the low temperature phase, that is the wild semi-metallic phase, and structurally it is the TD or orthorhombic phase. And when we talk about Raman, so it is the structure that we are really probing in that sense. Now, we just saw that there is a hysteresis in transport. So what about in Raman? So we probed this, and we could look at that one of these modes. I just mentioned that this P6 splits into two modes over here at low temperature. So that's what we specifically followed, and we could see that at high temperature, so this has a single component, and as we go to the low temperature, this very nicely splits into two. And not only that, as we raise the temperature from lowest to the highest, we see that this mode again disappearing. And interestingly, we see that the appearance and the disappearance temperature of this mode is not the same in the heating and cooling cycle, and that's what is related to the hysteresis discussed in the transport data. So we plotted here not only the intensity of the two modes as a function of temperature, which is given over here. So this is the 6B, that means the left one, and the right one is the 6B. So 6A and 6B, the intensity, as you can see, it shows a hysteretic behavior with temperature. And not only that, even the Raman frequency of this vibration also shows a clear hysteresis in temperature. So, so these are the signatures, and we know that this phase transition is first order in nature. Now, you see, I mean, of course, ours is not the first report in terms of the hysteresis seen in intensity, because so this article in Nature Com in way back 2018, they showed that there is a hysteresis of this mode, and here is the intensity that shows the hysteretic behavior. We added with this interesting observation of hysteresis in frequency as well as the line width, as we can see in this inset. Now, we also looked at the various other phonon modes. As we said, there are 9 different phonon modes, and we saw that all these other 9 different phonon modes show a very usual thermal behavior, which is basically the frequencies show the thermal softening of the modes. On the other hand, the line width shows kind of usual thermal broadening, and that is typical normal. And one can understand that if, let's say, I assume that it's a diatomic molecular system, it's just for understanding sake, and this is a spring ball model, and if it is the equilibrium state, so at higher temperature, what happens, the expansion happens in the lattice. So basically the K, the spring constant decreases, and at lower temperature, it becomes stiffer, so the spring constant becomes higher. And we know the frequency goes proportional to square root of K by M. So the K basically is the key player over here at high temperature and low temperature, right? And as it softens or hardens, so the frequency basically shows the same behavior. So basically in other modes, there is no surprise. But then the interesting thing that we observed was in one of the very low frequency mode. If you recall, this is the spectrum that we saw in previous slide, where this is one of the modes that's where we saw something very interesting happening. And this is the P1 we call as, and it's somewhere around 70, 80 wave number. Now let's look at what is the interesting feature that we saw. Now, before we go into the data, I would like to request you to focus on the insets of this frequency versus temperature plot. As you see, and we also discussed for the other modes, that as we increase the temperatures, the frequency should decrease for a phonon, which is what the enharmonic model would predict. And similarly, if you look at the line width of the mode, so it will go as increasing with increasing temperature. So that is what is expected. But on the other hand, for this crazy mode, the P1, it shows exactly reversal behavior. So you can see with increasing temperature, the frequency shows an increasing trend. But on the other hand, the line width shows decreasing trend. So that's very, very unusual. And this is what we're referring as phonon anomaly in this. And this anomaly in this system, if you just one by one try to look at what are the possible reasons, the only thing that can explain is the electron phonon coupling. And without that, we cannot explain this anomaly in the phonon. So here we would like to kind of emphasize that this anomaly in the phonon is because of the electron phonon coupling in the system. Now, so the example, the data that we just discussed so far is on bulk of the crystal. When I say bulk, that means it is many layers in it. It's basically very thick. Now, what if we thin it down? The usual way to achieve is micromechanical exfoliation, and we did that. And here are typical pictures of our the exfoliation. And here are some AFM data for reasonably thicker samples. And now let's look at, before we go into our data, based on as we go from very thick to thin layers, let's see what is already known in the literature. I mean that happens when you thin down this MOT2. So this is something very interesting. As you can see, if you recall that P6 mode that we had labeled, right? So this is that high temperature phase. And in the high temperature phase, if I remind you that it has only single component, but in the low temperature phase, it is supposed to have two components. And that is the signature of the phase transition, right? And this you can see, these people, they showed that for 50 nanometer film, I mean 50 nanometer thick layer flake, it shows this phase transition. But then as they thin down to below 20 nanometers, so here are examples that they have given, like below 12, 8, and so nanometer. As you can see, this at room temperature itself, it shows that this particular mode splits to two components. So what it basically establishes that even at room temperature itself, the MOT2, when it is thinned down, it becomes, or rather it gets stuck in the low temperature phase, which is the while semi-metallic phase, okay? Or rather, I would say that it is the orthorhombic phase. So which is what they established. That means if we thin down it, even at room temperature, it goes to the orthorhombic phase or the TD phase, which is the while semi-metallic phase. And this was, this PRB article which they showed. And the claim was like anything less than about 10 nanometers or so, the phase transition is completely quenched, and basically appears even at room temperature, which basically tells that the TD phase or the while semi-metallic phase is stabilized even at room temperature and all temperatures rather. So that is something which is known in the literature. Now let's see what we find. So here are data for various thickness, starting from the reasonably thick. So I call reasonably thick, so which is about 50 nanometer. And as if I remind you, the 50 nanometer, they show that there is phase transition across the temperature. And then 20 nanometer, 10 nanometer, and then we have these various thicknesses. And these thicknesses we get based on the Raman signature of this mode, and there is one more mode. And based on the shift of those modes, we can very nicely estimate what is the number of layers of that sample. And somewhere there are some ambiguities. For example, so here we say it is 4 to 5 layer. This is 5 to 6 layer. That's where the differences are very small, and it might be difficult to really predict whether it's 4 or 5 or this is 5 to 6. But okay, this is a limit that we can stick to at the moment. Now let's see what happens when we probe this over temperature. Here we're showing at room temperature. The middle panel is the room temperature data, and we can see there is a clear single component over here. Of course, you can see there is a slight broadening over here, which let's see in the next few slides. So, and then as we go to the low temperature, which is the minimum temperature in our case 80 K, you can see 50 nanometer flake shows the splitting, very clear splitting, which is what the signature of the transition of the phase transition. But then 20 nanometer shows still visible splitting of the mode, and then 10 nanometer.
You have 5 minutes more.
Oh, okay. And that
5 minutes of talking time.
Sure, sure. And then the other thicknesses, I can see the phase transition is lost. So that basically establishes that we also see that phase transition is lost. But the contrary to what they said is the phase transition that, or the phase that they showed was the TD phase, which is the orthorhombic phase, but in our case, it is the high temperature phase, which is the monoclinic phase, right? So that is what the contrasting observation that we have in compared to the previous data that we show. Now, question is, why is it so? So is it due to charge doping? So just to give you the information that our exfoliation was in air, and now let's see what some other people also predicted theoretically. So here is what an interesting prediction, that if there is a charge doping in terms of, let's say, electron to hole, so in the hole dope system, it will be the 1T prime phase, which is the high temperature phase, will be favored. On the other hand, when it goes to neutral or let's say electron dope system, it is the low temperature phase which will be favored. So that basically gives us some ideas now what could be happening. Now in the earlier article, if you really see, this particular exfoliation was done in nitrogen atmosphere, and that makes us very clear that in nitrogen atmosphere, you basically can only prime phase, which is the high temperature phase, will be favored. On the other hand, when it goes to neutral or let's say electron dope system, I'm getting my voice again.
Yeah, Devalina, can you please check? Can you please mute the others? Yeah, sorry.
Okay, so now there is another article which is again a theory which says that as we thin down, so there are inevitable defects, the tellurium defects that are formed, and that defect leads to electron doping in the system. So that basically explained in this article that due to exfoliation, when the tellurium deficiencies occur and that leads to electron doping, they would have achieved a situation where it was electron dope system, and that is why they could see the TD phase at room temperature or at any given temperature. And but on the other hand, in our case, it is the hole doping, and how we, let's say, so there are many other articles in two-dimensional materials, for example, graphene, sulfide, selenites. They show that if it is exfoliated in atmosphere or it is exposed to atmosphere, it usually goes to hole doping, and that's where we say that it is the hole doping due to atmospheric contact that is making our sample or the flakes to get stuck to the 1T prime or the what do you call the room temperature phase, even at lowest temperature. Now, how do we dope? So this is basically, now let's look at what happens. So that was the whole doping case. What if, we do intentionally electron doping? Of course, one can definitely look at in terms of, gating and see how one can, switch from electron doping to hole doping and see this. And since we did not have the fabrication facility, so we could not really look at. Instead, we took, some simple measures. So here we exposed our flakes into ammonia vapor, and ammonia vapor is known to electron dope system. And this is another example by rhenium doping, which I'll show in a couple of minutes. So upon ammonia exposure, which we know that it electron dopes the system, we see the clear splitting of the single mode into two mode, even to very thin layer. So here is the 2-layer sample, 3-layer sample, 5-layer sample, and so on and so forth. As you can see, right at room temperature, all of them shows the clear signature, and that basically establishes the other article as well. That means if it is electron dope, it basically shows the splitting, which is basically the orthorhombic phase. And if it is hole dope, it gets stuck to the monoclinic phase, which is what I showed in the previous data. So that's basically the result. And now we also did another way of electron doping, which is the rhenium incorporation into the ammo sites, and that gives electron into the system, and also it will give lattice strain in the system, and it will have some other effects as well. But let's see what is our observation. As we can see, we have experimented very thick to very thin down to monolayer, and we can see still a very, very clean splitting of this mode into two. And that again establishes the phase transition, and even down to a monolayer. And now here is what Ravi's group also showed, that with rhenium doping, there is an increase in the TC. This particular MOT2 is known to show superconductivity at very low temperature. And with rhenium doping, they showed that there is an increase in the TC. And so that's where interesting thing happens. And now let's look at quickly what happens in the phonon anomaly or the electron phonon coupling that we hit upon. So here is the electron phonon coupling, just to remind that the change in the phonon basically tells us. Now here we show at different layers how this behavior is changing the trend. So here is the very thick layer, and then as we thin down, I can see in the mono layer, so this is for the pure MOT2, not the doped one. In the pure MOT2, we see that in the thin layer sample, we basically see the reversal of the behavior. And that basically tells us, if we estimate, this delta, the change in the phonon frequencies temperature, and gives us, a measure of the electron phonon coupling, we see, reasonably thick films have, quite reasonable electron phonon coupling, but a 2-layer probably, basically becomes, it gets compensated due to inherent, hole doping, and exposure to the atmosphere. And then in 1 layer, it basically gets entirely electron doped. So we look, so here it basically shows the, the loss of electron phonon interaction in this system. And now we look at the rhenium dope system, and we see that, almost done. So in the rhenium dope system, that this electron phonon coupling prevails down to 1 layer, and that probably could also say a possible in a connection where the superconductivity temperature increases, and probably this is where also this electron phonon coupling is connected somewhere. And now this is where I'm going to draw the conclusion that we can find a way now to change the phase transition or explore the phases simply by hole doping or electron doping, even without really changing the temperature of the system. And that's what I try to say, that phase transition at will. And here are the the results of our pure system. We showed that the topological phases phase transition is suppressed when we exfoliate, and then depending on the environment, it will environment it is exposed to, it can get stuck to the wild semimetallic phase or the quantum spin Hall phase. And then electron phonon coupling is is there and has a very interesting role. And in the rhenium dope system, we see that the phase transition is preserved even in mono layer. And with that, I would like to thank all of you, and thanks again for listening to me.
Okay, thank you, Professor Shah, for very interesting talk. So the session is open for questions. So I can see Gautam Sheet has a question. Maybe you can ask that question.
Yes. MOT2, the low temperature TD phase, it shows a superconducting transition below about 100 millikelvin. Now that you can stabilize this in some way at very high temperature, did you also check what happens to the superconducting phase? Is it with rhenium doping, clearly the critical temperature goes up, but when you thin down MOT2 without any rhenium doping, what happens to the superconducting phase?
Well, as I said, we really fall short of this fabrication facility, and as you know, when we thin down, we really need to have prepare right devices, and we don't have the facility, so we could not yet explore this. Let's see. Hopefully, we'll be able to explore in the future in some way or other.
Okay, so nobody else did this experiment elsewhere?
Ravi is in contact with some people, so I don't have the update whether we already have some data or not. But I remember your work. I could have actually discussed. So the electron phonon coupling that we were just mentioning, and I remember Gautam, you also showed the charge density wave data in rhenium dope system. So we are thinking like whether it has some connection in this. So so we don't have the update in terms of the superconducting temperature, how it goes with exfoliation.
Oh, okay, thank you. Yes.
Okay. So maybe one last question by Priya.
Yeah. Can you hear me?
Yes.
Okay. So what is the nature of this? I mean, what is the structural difference between this 1T prime and TD phase? Is it associated with the stacking? If that is the case, then what kind of coupling are you talking about? I mean, it's an interlayer coupling that you're talking about, the electron phonon coupling?
Well, that needs to be, needs to have some further thought to really say.
Or rather, you showed some phonon mode behaving anomalously, right?
Yes,
so
yes.
What kind of atom vibration, I mean, do you know?
Okay, so this vibration, right. So this vibration is basically slightly off plane.
Okay, but it's not related to some coupling between the two layers, you're saying?
No. So, I mean, okay. So if, let's say, we exfoliate, right? And if it is related to, let's say, some sliding motion of the layers, this mode, I mean, layer motion would vanish if you go to single layer.
Yes.
Right. So that is not the thing here. This particular mode is present even down to monolayer. So it is just because of the vibration of the atoms in individual layers, and that vibration, if you really look at the eigenvectors, it is slightly off the plane.
Okay.
It is not a sliding motion or shear or breathing type. It is not that.
Okay. Yeah. Thank you.
You're welcome.
Atin, you've muted yourself.
Sorry, I have a short question. So I just want to say, you told that quantum spin Hall phase in the high temperature, right? So in the bulk, how can you say quantum spin Hall effect, right? When you are talking about bulk data, resistivity data, you are taking quantum spin Hall phase to this phase. So you cannot talk quantum spin Hall effect in bulk, right?
Sure. You see, I mean, I wanted to give this disclaimer in some way or other. So this quantum spin Hall phase and the phase transition, it was initially proposed in theory. And, there is Pashupati's group who showed that there is this phase transition that goes from quantum spin Hall phase at room temperature to the this what do you call the wild semi-metallic phase, and so bulk means it is basically few layers. I would say it is it is not just a monolayer. Yeah.
Surajit? No, that is Indro Neil. This is a theory guy. See,
Pardon? Pardon? Sorry.
Surajit.
So yeah, I think it's fine. So thank you, Professor Shah, for very interesting talk. So we'll move to the next talk now.
Sure. Thank you so much, Atin, and thank you, everyone.
Yeah, thanks. So maybe Shubhankar, next talk will be given by Professor Shubhankar Vedanto from NISA Bhubaneswar, and he will talk about some spin pumping and inverse spin Hall effect data. So yeah, Professor Vedanto. Yeah, we cannot hear you.
Shubhankar, you're muted.
Yes. Can you hear me now?
Yes.
Yeah, we can hear you. So I'll warn you at 20 minutes. Okay.
Yeah, please just ping me.
Thanks.
So
you do the
you
full
see
screen.
my screen?
Yeah, it's fine.
Okay. So good afternoon, everybody. It's a real pleasure to be part of this QMAT, and I thank all the organizers like Atindra, Manoranjan, and Priya for giving an opportunity to present our work. So today I will be talking about this spin pumping and inverse spin Hall effect with topological insulators and antiferromagnets. And as I said, I'm really grateful to QMAT because it was a nice platform. Can you hear me, or is there a problem? Atindra, can you hear me?
We can hear.
I can hear you.
Okay, so because sometimes I get a feeling like nothing is moving.
Oh, we are with you.
Thank you. All right, let's continue. So the point is, I really thank QMAT people for giving my group a good opportunity to present several talks. So yesterday, my postdoc, Dr. Polasman, talked about the spin liquid behavior in barium ruthenium substituted this compound. Just two talks after, my PhD student Purvasa will talk about spin pumping with fullerene, which is very interesting because this is a low spin orbit coupling material. And now I'm talking about topological insulators and antiferromagnets, which are good alternatives to heavy metals because they also exhibit high spin orbit coupling, and they're very interesting materials. And tomorrow, another PhD student who's a postdoc now with me, she will talk about exchange bias with iridium manganese and nickel manganese. So this is my group actually who do the work. So today, so mostly I will show the results from Dr. Brajbhushan Singh, who was a postdoc with me, and now he's an inspired faculty in our group. He's really a dynamic guy working on topological insulators and these interesting antiferromagnets. Then Kaustubh Roy, he is another PhD student who is working on this iridium manganese, and Puspendra is working on manganite based systems. Abhishek is working with chalcogenide based system, and Biswajit was a master student who worked with this iridium oxide, which is a very good new material for spin pumping. And there are a lot of collaborators, and for today's work, mostly I can say we are really happy to collaborate with Professor Kanishka Biswas from JNCSR and Dr. Biswarup Satpathy from SINP and Professor Thomas Buchel from Germany. So, so this is the basic outline of my talk. So, when we are talking about the spin to charge based spintronics, we need a ferromagnet and we need a non-magnet on top of it, which should exhibit high amount of spin orbit coupling. That is basically the bottom line. And mostly, if you see, the heavy metals are considered to be the non-magnetic systems, which possess high amount of spin orbit coupling, and such as platinum, tungsten, tantalum. So I think today Sunil Nair gave a very nice presentation on spin Seebeck effect. So he introduced these concepts. So, and we are taking platinum as a preferred material, and we are exploring new type of ferromagnetic systems. So, if you see, people mostly have taken permalloy or cobalt or some other ferromagnetic compounds, and we have taken recently this new Heusler alloy compounds, and we show that the CFMS with platinum actually exhibits probably the highest spin mixing conductance. That is in this archive paper is under review. And similarly, we also saw these manganites LSMO with platinum, where we have shown that it exhibits both spin pumping and anti-damping. And then another interest in our group is to look for alternative of heavy metals. In that respect, topological insulators come to a rescue. So that topic I will cover today. But there are other topics like iridium oxide, which is actually having much higher spin orbit coupling than material. Chalcogenides, they also exhibit high amount of spin orbit coupling, and this low atomic element carbon based compound C60, although it should not exhibit high spin orbit coupling. However, Purvasa will convince you why we can also observe such effects. And then another alternative to this heavy metals such as platinum would be antiferromagnets, because they actually exhibit high amount of spin orbit coupling, and you find more antiferromagnets in nature. So they're actually quite interesting also due to terahertz application and so on. So let's move on. I think very quickly I can cover that already Sunil has discussed this morning. This effect of, we all know the simple Hall effect. You take a metal, you apply magnetic field, and charges developed at the edges. So you can basically measure a voltage. Now, if you take a ferromagnetic film, then with similar mechanism, you can also get the so-called anomalous Hall effect. And there are various mechanisms like the skew scattering, side jump mechanism, and so on. So just imagine if you do the same type of measurement, but without a ferromagnet, so it is just a metal, then you have the pure spin Hall effect. So that you can simple have spin accumulation at the edges, and that's and now obviously there are many more spin analog of different charge based effects like spin Seebeck effects, Will Peltier effects, and so on. And this is basically the concept of charge current, spin current. I think I can skip it. This has been already discussed. What happens if you take a non-polarized current and spin polarized current, fully spin polarized current. So you have a charge current, but in this case you have a charge current of 0. However, you can have a full spin current. That's basically the advantage. And just quickly, the idea is that all elements, the spin orbit coupling is varying to z to the power 4. So that's the reason why heavy metals are actually having a high spin orbit coupling, but the problems are usually they're quite expensive and not too many options, unfortunately, in the periodic table. So you need to really search for alternatives. And the alternatives, I will discuss a few today during my lecture. So, okay, you can find like people have calculated the spin orbit interaction in various materials. Now, how you generate spin current? Spin current. Many people who are not working in the field, they sometimes feel charge current is movement of electrons, so spin current is really movement of spins. So answer is no, because it's basically the movement or the flow of angular momentum, spin angular momentum, and that you can say just dissipation happens from one side to the other. That is how you generate a spin current, and that you can achieve using the ferromagnetic resonance in a material, where you can write the Landau-Lucid equation in this form. And these slides are kind of repetitive. I'm sorry, Sunil, but thanks to you that you have explained it. So spin Hall effect, you have a metal and you pass a charge current, and because of this the sort of imbalance in the potential for different spins, so they will move to different edge of the sample. So there will be, let's say, up spins agglomerating at the this edge, and that edge would be the down spin. So you have a net spin current, and that's basically spin Hall effect. But unfortunately, you cannot really directly measure spin Hall effect because measuring spins, it's very challenging. Well, you can measure optically, but it's much more complicated, I would say. So to overcome this problem, you can actually use the inverse spin Hall effect, which just assume the similar concept. But imagine you have spin current in a material, and if you just imagine the charge imbalance in that, so the charges will be now agglomerated at the edges, and that will lead to a voltage, and that's basically will directly give you information of the spin current. And very important parameter is the spin Hall angle, which is much really important for the application point of view. It's the ratio of spin current to charge current. That means how efficiently you can convert between the charge to spin. And spin pumping is an interesting phenomena when you have a ferromagnet, um, and you have a non-magnetic substance. It can be heavy metal, it can be an antiferromagnet having spin orbit coupling, it can be topological insulator, it can be a chalcogenide, or any other material which can exhibit high spin orbit coupling. Even people have shown it can be another ferromagnet, then also you can get spin pumping. So basically, you excite the spins in the ferromagnet using ferromagnetic resonance, and then you pump the spins from the ferromagnet to the non-magnetic side. So this is like a spin source, and this is like a spin sink, and then you detect it, and that's basically the whole idea of spin pumping, because spins are getting pumped. And by that, if you measure the damping of the single layer and the damping of the bilayer with this heavy metal or any other material, you will see that damping gets enhanced for the bilayer system, just because there is a spin pumping. So I think this slide I can skip. So this is basically the schematic of our ferromagnetic resonance spectrometer in our lab. So it is with a CPW, so coplanar waveguide based system. You mount the sample in a flip chip manner, so like the top surface goes to the bottom of facing to the CPW. You excite with RF field. There is a Helmholtz field by which you measure this fMR spectra as a function of magnetic field. Then you will have a resonance. You can use the Kittel equations, and then you can extract the damping parameter, line width, and so on. So the same one you can basically use for this inverse spin Hall effect. Yeah, you put the sample, you do the same experiment. Now the small modification what you make is you put contacts at the edges, and you basically connect to a nanovolt meter, and you measure this voltage which is arising because of this spin current. So basically the spin to charge conversion. Okay, now as I said, so there are several like possibilities or several alternatives to the heavy metals, and one of them is topological insulator. There are plenty of talks I have seen in this conference, and everybody knows, but just uh, in case somebody does not know, it's a special material where the bulk is like insulator and the surface is metallic like, because there is a small a strong spin momentum locking at the surface, and that exhibits a very nice metallic state on the surface, and that can exhibit high amount of spin orbit coupling. That's actually the basic message. And then the question is, if it exhibits high amount of spin orbit coupling, then it can actually exhibit high amount of spin bumping. And there has been already some reports, very nice papers here, a breakthrough paper where they took bismuth selenide and they did the STFMR, and they showed that spin bumping is possible. However, all these papers mostly have taken the bismuth selenide, which has been prepared by um, um, molecular beam epitaxy, which is a much more involved technique and expensive. There has been, of course, some papers where people have prepared bismuth selenide with thermal evaporation. However, our approach was a bit different. We tried to deposit the bismuth selenide by electron beam evaporation, and I think we were the first to achieve it successfully. The difference is if you do by MBE, then you can achieve this epitaxial bismuth having nice punctuples. However, in our technique, we get kind of polycrystalline films. However, if you see the planes, it's all 003 planes are coming very nicely. And, we found there's a little bit of selenium vacancy, but that's actually pretty much the same even in MB prepared thin films. Now, to know more about these films, we did transmission electron microscopy with the help of Dr. Biswarup Satpathy. So we found that the bismuth films are actually polycrystalline, and but making these line scan analysis, you can understand a little bit more about the structure of bismuth, and then the transport properties, which indeed evidence the topological nature of the material. And you do simple R versus T, where you see that the you get a metallic phase, then below 50 Kelvin you are seeing this kind of upturn, which indicates this weak antilocalization, very typical for topological insulators. And then in the transport property, you get really nice behavior. We got about 10% MR, and I think until our paper was published 2 years ago, the other people have observed about 7%. So in their MB grown film, so we don't know exactly why these polycrystalline films are exhibiting a little bit higher MR, but the values are indeed comparable in the same order. Now let's try to understand the damping of the single layer as well as the bilayers. So you take the single layer of cobalt iron boron, you find the damping value is like 0.03. Then you take the bilayer, and there is a little bit enhancement of the damping constant that indicates that some spin pumping is happening, but it is not a direct evidence, because there may be other interface phenomena which can still increase the damping, but it is not necessary to be spin pumping. In order to conclude or understand more about the spin pumping, we did this ISHE measurement, so inverse spin Hall effect, and then we found beautiful signals. So this red curve is basically the FMR spectra, and these blue data points are basically our ISHE. And you can also rotate the sample, and this blue curve should change its sign. So that clearly indicates that it's a spin pumping. So we did that, and here we just show a reference sample of the single layer, and we see no spin pumping. So it clearly shows that with bismuth selenide you get a beautiful spin pumping voltage. Then obviously that signal you can disentangle into the symmetric and anti-symmetric component, and and that's basically right here. And you can use this formula to decompose the symmetric component and asymmetric component, and the symmetric component contains this spin pumping voltage and this anomalous Hall effect, anisotropic magnetic resistance, and other effects, and the asymmetric components, the other spin rectification effects. So the point is, if you make an angle dependent over 360-degree, really 2-degree steps, and you plot the V symmetric versus angle and the V asymmetric versus angle, using these formulas, you can now figure out the individual components. So we find the spin pumping voltage is the highest among all other spin rectification effects, and that's really nice that the bismuth selenide prepared by electron beam evaporation is actually exhibiting definitely high spin orbit coupling, which finally leads to this inverse spin Hall effect. Atindra, how much time I have?
So you have 18 minutes over, so you can speak 7 minutes more.
7 minutes. Okay, thank you.
Yeah.
So now we wanted to, of course, that paper basically 2 years ago we published, and Braj was very happy that this paper was one of the top downloaded paper of PSS Rapid for the year 2019. And then we tried to understand a little bit more that the bismuth selenide, what we have prepared, is it, it's the more surface effect or more bulk effect. So that the inverse spin Hall effect is more bulk, and the the Rasbay-Edelstein effect is more surface. And to elucidate that, of course, you need to prepare a thickness dependent study. So where we fix the ferromagnetic thickness. Cobalt iron boron is a beautiful material having low damping, and bismuth selenide, here we have varied the thickness from 3 to 20 nanometer. These are the XR curves, which shows the layers are good quality. Then again, the similar things that we measure the spin pumping, and as I was saying, the 0 degree, if it is exhibiting this voltage like that, then if you rotate the sample by 180 degree, the sign should change, and if you go, let's say, to 90 degree, it should be a very minimal signal because it will cancel out, and that's basically shown here. Then we evaluated for different samples how much is this voltage, and I think this plot, this plot is more informative, where you plot the effective damping constant as a function of small solenoid thickness, then the spin hole angle as a function of thickness. I think this plot is very useful, this spin hole angle, which shows that there is not a very linear trend. Usually, if you observe the spin hole effect, mostly the theta sh should decrease as a continuously as a function of thickness. But here you have an increase and decrease that shows that it's not really from the bulk, it is rather from the surface. And that surface, then it is the Edelstein effect, and this efficiency, spin to charge conversion efficiency, SCCC, you define as lambda inverse Rasby-Edelstein effect. That is basically the Jc by Js in this case, and you can calculate it. And the G effective, also the effective spin mixing conductance, which is another important parameter, it is actually behaving like that, so it's this is not following the spin diffusion theory. And but one important message of this manuscript, which is under review, is the surface anisotropy. If you plot as a function of thickness and the 4 pi effective, it actually behaves very similar. So that shows that the the inverse Rasby-Edelstein effect is more prominent in these samples. So this basically comes from this surface Dirac states. Now I go to quickly to the second part of my talk, which are antiferromagnets. And I think we have seen in some slides that antiferromagnets are interesting but useless, as has been claimed by Professor Neil in his Nobel lecture. But that situation has changed in last couple of decades. And now we know that antiferromagnets are very promising materials because they don't have any magnetic moment, they don't have any stirred fields. So basically they don't do any crosstalk, and they are very efficient for high frequency applications because they exhibit the terahertz radiation. So they are very, very interesting material for spintronics. And now, as I said, that these antiferromagnets also exhibit high amount of spin orbit coupling, so they can be used as this spin hall effect studies. And antiferromagnets you can broadly classify into collinear and non-collinear antiferromagnets. Collinears are like manganese gold, iridium manganese, nickel manganese, so on. Non-collinear, there are this iridium manganese 3, manganese gallium, and Mn3 gallium. So the manganese gold is a very interesting new antiferromagnetic system, which has very high Néel temperature. And recently it has been shown that you can actually do the control of the Néel spin orbital torque. I'm not going into detail. This is an electrical control of the Néel spin orbital torque, and so on. But we focused, I think, more on the spin Hall effect, which was not done. And we took again the manganese gold. This is an antiferromagnet, cobalt iron boron ferromagnet, and we grown nicely the manganese gold by sputtering, and we found that it is actually indeed leading very high amount of spin pumping. And by doing similar analysis, what I have shown earlier, by fitting these functions for symmetric, asymmetric, you can actually disentangle the spin pumping voltage, the anomalous voltage, and so on. And we find the spin pumping voltage is more, and you can indeed calculate the spin hole angle of this manganese gold. And we have shown the highest spin hole angle in any collinear antiferromagnets, because usually for collinear antiferromagnet like iridium manganese, nickel manganese, the spin hole angle is like 0.02 to 0.01 or something like that. Okay, so this is another compound, iridium manganese, which has already been done from the group of Axel Hoffman. So they have studied for formalloy, but we try to focus on this interesting ferromagnetic material, cobalt iron boron, and with iridium manganese, but we put a special layer of copper so that you don't have direct exchange coupling, so that no exchange bias. And we try to see, and copper has high spin diffusion length, so you can still interact and pump spins basically from the ferromagnet to the antiferromagnet.
Shubhankar, you have 2 more minutes.
Okay, fine. So then you measure the damping constant for the single layer of cobalt iron boron and the bilayers, and you plot this, and you find there is an enhancement of damping constant for about 0.5 nanometer, and that goes very well because in literature for iridium manganese the spin diffusion length is about 0.5 nanometer, and that we kind of show it. And further we did also the ISHE measurements, and we decompose, and we found the spin pumping voltage is higher compared to other spin rectification effects, and we found that the spin hole angle for our system is little bit higher for the reported value, where they have taken permalloy as a ferromagnet and we have taken the cobalt iron boron. However, the spin mixing conductance is comparable, is 5.8 10 to the 18. That's in the same order of reported values, and the spin diffusion length is about 0.7 nanometer, which is also in the same order. Now, just last 1 minute, I would like to spend on these very interesting collinear antiferromagnets. Some of you may know that this iridium manganese 3 IRMN3 is a recent discovered, antiferromagnet, and a lot of research happening on the similar compounds where it's Mn3X basically, SN, Ge, gallium, and so on. So we have focused manganese gallium, and we have prepared successfully the manganese gallium films. Here the X-ray is very nicely, we show that the manganese gallium is happening, and I don't have much time, and we have taken again cobalt iron boron as a spin source, and we try to do the spin pumping. Here the frequency dependent of the voltage, and we do some analysis, and we found that this the spin hole angle for this system, that's I think the take home message, is about 0.52. So in percentage you can say 52% spin to charge conversion is happening. That's really remarkable for the system, because the iridium manganese, which was published in Science Advance by Stuart Parkin group, it is about 0.35. So here manganese gallium is showing much higher values. So I think with this I am almost done. I hope I have convinced you that the topological insulators, antiferromagnets are really good alternatives to heavy metals, and in terms of economy, as well as there is a much better spectrum of materials where you can really do a lot of rich physics, and they're really nice materials for future spin tuning applications. So with this, I like to thank everybody, and I'm really looking forward to the talk of Professor Mighty, and thanks to Surjit for setting the train. Thank you.
Okay. So thank you, Professor Vedanta, for very nice talk. So now the session is open for questions. So I can see if you have raised hand or someone. If there is any question, you cannot see any question in the box.
There are no questions.
So I have a question. So I just wanted to ask, have you done any transport measurement or like inverse spin Hall effect, what you are measuring through transport in these devices?
Okay, you are asking about the electrical measurement.
Electrical transport.
ISHE.
Yeah.
No, we are mostly focusing using the FMR, but I think we are now making a setup. So where we will do the spin orbital torque measurements, and in principle we will be able. Our FIB is just getting installed. For that we really need devices, and so hopefully maybe in a year time we will have also the electrical measurement of that. Yeah.
Okay. Now I can see that Avik Beat has a question. So Avik, can you please?
Yeah, hi Avik, go ahead.
Hi. Nice talk, Shubhankar. One quick question. This is related to what Atin asked. Can you estimate what is the coherence length of the spin coherence length of these systems?
Well, we have not focused into that, but in principle it can be done. We have calculated the forming velocity, the relaxation time. In principle, that can be done.
Okay.
Okay. We have not focused on that part.
Because from your data, it looks like it should be significantly large, right? Because from your coherence length, times are large, so.
Yeah, I agree, but yeah, thanks for asking this question. I hope next time I will come with some numbers. Yeah.
Great. Thank you so much.
Yeah, thank you.
I have a quick question too.
Yeah, please.
Shubhankar, in this polycrystalline sample, when you talk about anisotropic magnetometry,
we cannot hear you. Yeah.
Gautam, I'm here. I'm sorry. Please go
The
ahead.
angle is measured with respect to what?
Okay, okay, basically you're asking this one?
Yes, for example, yes.
Oh, yes. So this is basically, can you see my video?
I can see
you. Yeah.
Okay, because I can see. Anyway, so it's like you mount the sample and you rotate the sample. Okay, in 360 degree. So there are contacts. The RF field direction and the CPW, they're all fixed, and you are just rotating the sample. That's called the angle dependent behavior. So by that you are actually able to disentangle all these spin rectification effects. Does it answer your question?
Okay, we will talk about it later, maybe.
Okay. So maybe we'll go to the next question by Professor Sunil Nair. Yep.
Yeah, hi, Sunil.
Shubhankar, nice talk. I just had a question about this is towards the fag end of your first half, where you showed the spin Hall angle having thickness dependence.
Yeah.
Why does this happen? I mean, you have this abnormal increase and falling down. Do you have any idea as to why this is happening?
Well, we don't know exactly why it is happening around 10 nanometer. So, but the point is that shows that is one indication that it is simple, not the ball contribution. It is more surface contribution.
Why are you saying that? I mean, how does this tell you that this is not a bulk contribution, but it's a contribution?
Well, I will tell you later.
Okay. Fine. All right.
Okay. So if there is no other question, I think it's fine. So, okay. If there is no other question, let's thank Professor Vedanta again, and we'll move to the next talk. Yeah, thanks.
Yeah. Bye.
So the next talk will be given by Professor Kalabaran Maiti from TIFR Mumbai. So he will talk about electronic structure of a non-centrosymmetric superconductor BIP. Right? That is his talk. Yeah, Professor Maiti.
You can see my.
Yeah, we can see and hear you as well. Yeah.
Okay. Just a minute. I have to. I'm just trying to find out the pointer.
So just right click on the screen. Please do the and right click and you will find pointed option laser pointer.
Okay, yeah. Now you can see the pointer.
Yeah, we can see. We can see. So I'll warn you at 20 minutes. Okay. So
okay.
5 minutes. Okay.
So you are seeing only one screen, not multiple screen, isn't it?
Yeah, one screen. Yeah.
Okay, fine.
That's fine.
Okay, great.
Thanks.
Anyway, thank you. So first of all, I like to thank the organizer for this opportunity to give this talk. And it's very nice that although there is this pandemic situation, but we are able to do it, and it's done in a very nice way. So, and hope all of you are very safe. Today, I will try to talk on the electronic structure of a BIPD, which is a very interesting material. I'll give you some introduction on that. And basically, I'll try to talk about the photo emission results without giving much important introduction about the spectroscopy. I assume that all of you are aware of this. Okay, so the work that I'll be presenting today, so this is my group. So it's primarily contributed by Arindam, so who is the final year student now. And the other people are, this is Ram, who has also contributed in this activity. He's working on iron-based superconductors. Then Shawnee is working on massive Dirac fermions. Then time-resolved RPS, Tanushree is working. And then these two are postdocs, so they also are working in similar kind of activities. But today, whatever I'll be talking primarily is the work of Arindam. And the collaborators are, so major part of the experiments are done at Diamond Light Source. So basically, I was participating from here, TIFR, and these two were, so Denis Valik and Alexander Generalov were doing the actual measurements. And we have done some experiments at Electra, where I was also there. So this whole group has essentially contributed there during the measurements. And the samples were prepared. So the extremely high quality samples, they were prepared by Professor Ramki, Thamizabel, and the financial support is from DAE, DST, and of course, thanks to Diamond Light Source and Electra for the opportunity to do the work. My mouse somehow is getting stuck, but anyway. As you know, I mean, there were a lot of talks on topological insulators and vial semimetals and so on, which is a extremely well discussed topic these days. So basically, without going into much details on the material aspect, the idea is that these materials are basically insulators in the bulk, means that it has a empty conduction band and completely filled valence band. And the surface states, they form a Dirac cone because of the protection of time reversal symmetry. Now, due to this time reversal symmetry protection, so what happens is that the orbital moment and spin moments are locked, in the sense that if an electron is moving towards right and if it has upspin, then the electrons which are moving towards left must be having a downspin, because the strong spin orbit coupling actually separates the energy level significantly, so that you don't have a spin flip scattering. So that's the most interesting property of this kind of materials, and that can be utilized for various applications as well as realize important, interesting physics questions. Okay, so many of the materials which are studied. So if you do electron spectroscopy, so these surface states that I'm talking about, so they show up like a Dirac cone. Okay, so like here, you have for Bi to Ac3 or something like similar kind of materials where you have a Dirac cone. So this point where these two bands meet is called the node, or Dirac node you can call it, and they essentially have effective linear dispersion. Now, a lot of activities going on, if you have, say, this time reversal symmetry protection as well as inversion symmetry protection, you can play around with this, whereby various doping and so on, you can open up a gap at the Dirac node, or you can do various other things. So that way, when there is a gap, then the Dirac fermions are sometimes called massive Dirac fermions, because essentially they are massless particles. But I mean, they don't really cross each other, although they are highly mobile kind of. Of course, the most interesting things which nowadays people have been looking at is topological superconductors, where I mean, people think that if you have superconductivity among the electrons, which also satisfy this topological protection, you can actually realize many interesting things. So one of them, which I'll be talking today, is bismuth palladium. So this is extensively studied by our colleague, Professor Ramakrishnan. So they found that they are the one, I think, first published showing that this shows superconductivity at a TC of about 3.8 Kelvin. And the crystal structure is such that if you are above 210 degrees centigrade, so then it's a orthorhombic structure, but if you are at room temperature or below, so then it has a monoclinic structure which doesn't have inversion symmetry in the crystal. So that means it's a non-centrosymmetric superconductor. So this kind of materials are very interesting because if you don't have inversion symmetry in the bulk, so the spin orbit coupling will lift the spin degeneracy of the bulk bands. So and of course, because of strong spin orbit coupling, you can have non-trivial topology. You can realize Dirac and Weil crossings, protected surface states, Majorana quasi-particles, and so on if there is superconductivity. So there are many possibilities that have been proposed. Of course, you can think of, like, since there is no inversion symmetry, So you can actually mix up spin, triplet, pin, singlets, pairing, and so on. So all these kind of interesting physics, as well as maybe possible applications in quantum technology and so on. So a lot of people are looking at materials which can show topological protection as well as superconductivity, and then see if the superconductivity and topological protections are linked to each other. So that's basically the idea. So that was basically the idea for which we also have been trying to look for new materials and see if one can find superconductivity among the states which shows topological protection, or the states which shows topological protection, they are linked to superconductivity. I mean, there is an interaction between them. So first, I'll show you some of the core level spectrum, which has a lot of implication in the band structure. So that's the reason I'm showing it first. And then I'll give you introduction about the band structure of this material without talking much, because we don't have much time in this talk. So if you look at the core level spectrum, so this is the crystal structure, which you might have noticed, but the core level spectrum shows that this is bismuth 4F and palladium 3D. It shows a lot of lost features due to plasmon, but main interesting thing is that it has a sharp spin orbit split palladium 3D peaks and bismuth 4F peaks. So let's focus on these two, which are very sharp. We have done a lot of experiment. What you do is that when you do photo emission, you know that this technique is a highly surface sensitive technique. So if you are doing, say, XPS with typical aluminum K alpha source or so, where the photon energy is about 1.5 kilo electron volt. So the effective probing depth is of the order of, say, 20 to 25 angstrom. So which is about 10 layers or so. Now, if you go to hard X-ray, like 6 kilo electron volt or so, so then your probing depth becomes much higher, like 40 angstrom. So then we assume that most of the bulk electronic structure can be probed. So now you can actually change the probing depth by changing the emission angle, so that if you are having normal emission of electrons, that has a highest probing depth, and then if you have grazing emission, then the probing depth is much lower. So that's the game that we play to find out surface and electronic structures. So here we see that if you do a normal emission and a 60-degree angled emission, they look similar. So as if the bulk and surface, they are somewhat similar in these materials. I wanted to look at surface even in the core level also, just to see, because the surface and bulk are expected to be different in this kind of materials. Okay. Now, instead of hard X-ray, let's use soft X-ray, or say extreme ultraviolet region. So there you see that same peak. This is bismuth 4F, and you can see that this 4F 7/2 peak shows two peak structure instead of a one peak that was seen in hard X-ray. Since hard X-ray is bulk sensitive and it matches with this peak, so we can think of this is probably the bulk peak, and there is a clear surface peak which becomes visible only when you go to low energy, where your probing depth is of the order of, say, 6 angstrom or so. So that means that in this material, the surface electronic structure, if it is different, they are actually confined close to the surface, like one or two layers. Normally, in many materials, if you look at the effective surface depth, that goes or extend beyond 2 to 3 layers or 4 layers sometimes. Like if you look at transition metal systems, so there can be of the order of, say, 10 to 12 angstrom. But here it's very, very narrow. And that's the reason you see that only when you become extremely surface sensitive, then you see surface and bulk peaks separately. And we can, of course, study it by changing photon energy and find out the effective penetration depth, where the maximum surface sensitivity is of the order of, say, 6 angstrom or so, at around 35 to 40 electron volt kinetic energy. Okay? So that's one thing. But the most problematic thing that we found is that normally, if you look at, say, bismuth 4F, so this intensity ratio of this peak and this peak should be, so this is 7/2. So if you make it 2j plus 1, which is 8, and this one is 5 by 2, this is 6. So the intensity ratio would be 6:8. So which is about 3:4. But we always found that this intensity is much stronger compared to this. So this is found only for bismuth, but we don't find it for palladium. Palladium 3D shows essentially 2:3 ratio. Now, if you make it more surface sensitive, you see that this intensity goes up. Okay, so this black line is actually more surface sensitive spectrum. So this is something which is unusual because normally you know that this effective quantum picture where the branching ratio means the intensity ratio between these two peaks should be 2j plus 1, where j is the total angular momentum, which is L plus S or L minus S. But here we see that that is not followed. So normally, when we were trying to think what could be the reason, and what we find is that because in the solid you have a effective electric field because of this lack of inversion symmetry, even in the bulk, which can give you additional contribution to the orbital moment. Okay, so which will enhance the orbital moment, whatever you have compared to the atomic picture, and we feel that that could be the reason for this enhancement of the branching ratio. Okay, so one thing is from the core level spectrum, it's very clear that in the bulk, the bismuth core level effective orbital moment is enhanced due to the enhancement of the orbital moment coming from this lack of inversion symmetry. Okay, and this effect becomes even stronger. Now you know that in the bulk, if you have this absence of inversion symmetry, you can get this Dresselhaus kind of term in your spin orbit coupling, and at the surface, because of the translational symmetry breaking, you have this Rashba kind of effect, which also might be enhanced if you have lack of inversion symmetry even in the bulk. And that probably is giving you additional effect on the orbital. So let's keep this in mind when we discuss about the next part. Okay, now let's talk about the topologically protected states. A lot of studies have been done. So now I'll just tell you briefly and very quickly what all has been studied. So this is the study by Zahid Hassan. So they have shown that there is so this one 0 is the gamma point, and this is your kinetic energy. The Fermi level is somewhere here, which is, so you can see that if I assume the Fermi level is at the 0 of your energy, which is in the color plot you can see here. So the Dirac states or the kind of Dirac cone that you can assume here, which is faint, and in this plot it is much more intense. So those states are actually coming at around say 0.7 electron volt binding energy, which is very, very far away from the Fermi level. So it means that although this material is superconducting, but the Dirac state probably is not really playing a role in superconductivity because their binding energy is much higher. The second thing is that they have done spin resolved photoemission, and they found that this one and this one, they follow the spin orbit locking. It means that if this one is upspin, so this one is downspin. So they are actually topologically protected surface states. Okay. Now there is another study by Andrea Damacelli's group. So they also looked at. Now you can see that they also find. You see the Dirac cone that has been shown here in the previous one, which is a expanded scale. The same thing if you do it in a, I mean, in this energy scale, it looks very, I mean, close to each other, but actually they are the Dirac states, which is shown by calculation also. But what they see that the Dirac node is appearing at a finite momentum, not really at the gamma point. So the gamma point is here. And this they have actually justified by calculations and saying that actually the Dirac states are not at the not at the gamma point. But of course, these are surface states that they have shown. And they find that this Dirac cone that you observe here, they have significant anisotropy. So anisotropy means that if you are plotting at this is the S point, which is the high symmetry point. So if you plot at S gamma and S gamma prime direction, they are different. Okay, so like here it is shown that in one K vector along it looks like this, in another K vector it looks like this. So the spin splitting of these states at a particular K point is different. So this anisotropy is coming probably because of the anisotropic Rashba effect. That's the thing they think in this, and they have modeled this. So this Kr is the Rashba kind of term, which is anisotropic in different K directions. Okay, so that's the explanation that they gave. Then, of course, I point out Shetty's work. So they have published a PRL along with DD and Fink. So you can see the quality of data is somewhat better in this case. And so what they again say that actually the Dirac node is at gamma point, not really at finite S point. And it of course shows the anisotropy. But their main interesting finding is that they show that this Dirac node that you see at gamma point, if you change the photon energy, there is a gap opening up. So it means that if you plot the gap as a function of photon energy, it looks like this. So now it means that if there is a gap, as if that these Dirac states, they are not really purely two-dimensional surface states, but there might be some link to the bulk. So that gives rise to this. But they of course cannot explain why this doesn't show periodicity. If this is a bulk like states, then if you vary kz, so when you change momentum as a photon energy, you actually vary kz. So it should show periodicity as a function of kz, which they did not find. So they found only 0 gap at 75 eV, and if you go in both sides, they decrease the gap. Okay, so this is one unknown problem that was there. Now this has been bothering people a lot. First of all, to identify whether this Dirac cone is appearing at gamma point or somewhere else. Because you know that if the momentum is different, then the symmetry arguments that you are using for the topological protection will be very different. Because time reversal symmetry at gamma and at finite momentum is very different. So this has been resolved by this paper, which is again, I think Andrea Damacheli and various other people, ERS co-editor. So they show that
Professor Mighty, you have 5 minutes more.
Oh, okay. So I'll quickly wind it up. Okay. Yeah. So they show that actually this kind of confusion is coming. You see, what you experimentally observe, that is an experimental fact that has to be identified. But the main thing is that in calculation also why you are getting this confusion. So they see that actually different people, when they do DFT calculation, they do different kind of unit cells. So 1 to P2 by 1 unit cell, this one corresponds to B21, which is a larger unit cell. So the corresponding Brillouin zone is smaller. And they show that actually if you have a smaller Brillouin zone, you force in a X point and Z point, which are not true the high symmetry point. Actually, the red one is the correct Brillouin zone. And so that's the reason you have a band folding. And this S point, wherever you are supposed to see the this Dirac cone actually folds back to the gamma point. So this is the error that is happening. Actually, the Dirac cone that is supposed to be appearing below the Fermi level are at the high symmetry point S, not at the gamma point. So that's something that they have shown here. Now let's address these two questions. One is this Dirac node location experimentally and the anisotropy of the Dirac bands. Okay, you can see that we have actually done extremely good, extensive study on these materials. Unfortunately, although our study was done much before all these publications came out, like 2015 or even earlier, but we have not published because it took much longer time to analyze, and in between so many publications came out. But we have done a thorough job, and the data quality, of course, we had the best, I can claim without any doubt. So this is shown here. You can see the bands, how sharply defined there. Now let's go to this point. Now we clearly see that actually this Dirac cone and which is there, this is one K vector, this is another K vector, and it shows that the bands are crossing. Okay, there is no gap at 55 dB. Now we can change this photon energy and see what is happening. So I'll should be a little faster because there is no time. So now what we have done is that in this case, we have optimized the experimental conditions at 35 eV electron volt and do the experiment. This is done at diamond. And you see that this is the EDC corresponding to this color plot, and you go to higher photon energy, a gap opens up, okay, which is plotted here. So you have a zero gap, and then it increases if you increase photon. Now, when you are doing at Electra, we optimized at 74 eV. We found the Dirac cone and then reduce the photon energy, and we see that go away from this optimized point, the gap opens up. Okay, so this is the opposite scenario. So this is summarized here. So whenever you try to optimize the sample position, you see that you are able to get the Dirac cone without any gap. So at 55, 35, 74, and if you go away, keep the sample at that position and change photon energy, and you see that there is a gap at other photon. So this shows that actually this finding of gap at the Dirac point is an experimental artifact, not really the property of the material. Okay? So what could happen? So if you are looking at the gamma point, of course, it's a 0, 0 point. So even if you change photon energy, which changes your kz vector, you don't really change the 0, 0 point of your k. So that way you should be having the Dirac node, I mean, satisfied at all the photon energies, but that's not happening in the experiment. So it clearly shows that definitely the Dirac node that you're observing, it must be at a finite k. And if you change photon energy, it scales the kz value. So kz shifts. So for example, if you have this cone and if you optimize here, if you increase photon energy, then your k vector actually go away from this node. Similarly, if you reduce, it goes away. This way, you actually can explain the data that SETI has published, and also all the other data people have published. We then looked at these EDCs at this S point, and we see that at different photon energy, you can see that the peaks are not shifting. So we found that this is a Dirac cone, this is another Dirac cone, and there are additional many surface peaks which are there, which correspond to the surface electronics. So the other things are which are, you see that they are bulk. Okay. Now let's look at the anisotropy. So if you look at this contour, constant energy contours, so at the Dirac, we have looked at this Dirac node and at different points. So now you see that at this point and this point, they are almost circular. Okay. So there is no anisotropy, but if you go far away from this node, you see there is an anisotropy, like C2 symmetry appears in this constant energy contours. So now, if you have isotropy close to the node and anisotropy far away, so this anisotropic Rashba coupling cannot really explain this behavior. So what we have done, we have actually constructed a Hamiltonian based on this observation, where we see that if you use higher order terms, this is a k dot p kind of, this methodology that you have used. So where 0 is your S point and any deviation from 0 is the kx and ky. Okay. So if you include these higher order terms, you can exactly capture the this band dispersion that we have found out, and the corresponding terms that you can see, this R and S, which gives you the higher order terms, which are quite significant. Okay. And you can see that close to the Dirac node, they are giving you isotropic. So this one is, these blue ones are along one k vector, the green ones are along another k vector. The symbols are experimental points, and they actually show the isotropy close to the Dirac node, but far away they are anisotropic. And the spin splitting, that means this is up and this is down, or this is up spin, this is down spin, whichever way you define. So this splitting, you can see along this vector is different from this along other vector, and we could actually capture all the scenario. Okay. So
yeah, maybe you can finish.
Yes, this is the last slide. So basically, you can also plot the spin texture using that Hamiltonian that I have shown. So what we try to say is that actually this is extremely interesting material where you see that the absence of inversion symmetry probably is giving you additional complexity in your spin orbit coupling. So probably this orbital moment is higher, and higher order spin orbit terms becomes important for this kind of material. Okay. So the conclusion that we can draw from this study is that the Dirac node that people have found out so far in various studies are actually occurring at a S point, which has a finite momentum, not at the gamma point. And the anisotropy that we will find can be explained by this higher order, which could be because of the lack of inversion symmetry in this material. That's our guess. But of course, we are looking at it much more in this material and trying to understand. Thank you very much. So if you have any question, you may please.
Thank you, Professor Maiti, for a very nice talk. So the session is open for question. So I can see only one question in the chat box. So Orko Bandopadhyay has asked, can you please unmute and ask the question? Hello?
Yeah, please. Yeah.
Is Orko Bandopadhyay is there?
Hello, sir. Yeah, am I audible?
Yes, yes.
Yeah.
Okay, yeah. Sir, so when we are looking at the zone folding effect in some experiment, like I can understand from DFT results that this is some different unit cell that we are choosing. But what is the experimental way to look at that? Is there some symmetry perturbation, like the symmetry has is somehow perturbed or something like that?
Experimentally, you get the true, Brillouin zone mapping. You see, if there is a zone folding, experimentally, you'll be able to find out from RPS. So, this normally, for example, if you have say density waves, these are good examples like SDW, CDW, and so on, or anti-permanency ordering. So, wherever there is a zone folding because of additional symmetry, so you often see the bands are folding back, there is an opening of gap that you can exactly find out from experiment. So here, experimentally, we find that actually the Dirac node that was wrongly identified at gamma point is not at gamma point, but at the S point. It was, from calculation, it was found at gamma because they used a bigger unit cell for their calculation. The moment you use a bigger unit cell, your effective Brillouin zone becomes smaller. Okay.
Right. Yes.
So that gives you zone folding. But
yes.
Our experiment, we have done really a detailed optimization and careful studies that I have shown in my plot, that if you optimize the experimental setup at different photon energy, you always land up getting a Dirac cone without a gap.
Okay.
So this means that it is not at gamma point. This cannot happen if you have the Dirac point at the Dirac node at the gamma. It's a 0-0.
Right. Thank
so
you.
This is a confirmation. Yeah.
I can see Priya Mahadevan has a question. So Priya, can you please ask?
Yeah, Priya.
Hi, Kalo. Nice talk. I
Hi,
just got confused on one point.
Yes.
Doesn't your DFT with the right symmetry get you your band dispersion? Because then why did you go to K.P? And with higher
No,
order?
it doesn't give the correct dispersion. That's the thing. So
because DFT will have all your higher order effects also. So that's why I'm a little puzzled, because what you get in because you have the spin orbit included in the DFT calculation. So that's why I'm a little puzzled why it doesn't get it.
Okay. No, okay, sorry, Priya. I think I was thinking something differently. You are right. The DFT result shows the anisotropic Dirac states. Yeah, that's correct. But why we went to K.P is really to understand what exactly is happening. What is the role of spin orbit coupling or this additional, what is the role of inversion symmetry and so on. So like that. Okay. DFT, of course, you do get the energy bands, which shows some kind of anisotropy in the Dirac nodes. That's correct.
Yeah. Okay, thanks.
That we have seen in the calculation itself that if you look at, say, S gamma direction and S gamma prime direction, so they are different. So that means the spin orbit splitting is, spin splitting of the bands are different. So there is an anisotropy, correct. So we went to K.P is just to understand, what is the physics behind. Okay.
Yeah.
Okay. So if there is no other questions, let's thank Professor Maiti for a very nice talk. So we'll move to next talk. So if you can stop sharing your screen, yeah, that's it. So next talk will be given by Priya Tiwari from IISc Bangalore. She will be talking about electric field induced band structure engineering in bilayer graphene heterostructure, realization of spin orbit valve spin orbit valve effect. Yeah.
Okay, hello.
Yeah.
Am I audible to everyone?
Yeah, you're audible, but there is some background noise. Yeah. Yeah. I think it's okay. You can speak. No, there is some background noise coming.
Is it now fine?
Still the noise is there, I guess.
I think maybe it's my laptop.
I think the internet connection could be an issue.
Hello.
Hello. Yeah.
Yeah. Now is it fine?
No, it's not. Means you can start. Maybe we can check. Our system, our sysadmin may help if they have some.
Maybe you can reconnect.
Yeah, you can reconnect. Yeah.
Yes. Yeah.
Disconnect and connect.
Yes.
Yeah, can you please disconnect completely and reconnect once more?
Or you mean should I rejoin this session?
Yeah, I think maybe that will be better.
Yes. Hello.
Hello.
Yeah. Now my voice is clear.
Still, there is a background noise.
Still, there is a background noise, but you can start maybe. Let's.
Okay. Okay. So I'm sharing the screen.
Yeah, maybe you can start. Yeah.
First of all, I would like to thanks the organizer for giving me this opportunity. I'm Priya Tiwari from Indian Institute of Science, and I will be speaking about electric field tunable Rayleigh-Jeeman effect in bilayer graphene heterostructure and realization of spin orbit valve effect. So first, I will quickly start with a short description about bilayer graphene. So bilayer graphene has this kind of lattice structure of carbon atoms, which is also called Bernal stacking, and this is how it naturally exists in nature. So in this side view picture, the pair of carbon atom in which the one atom is lying exactly on top of another is called dimer pair, and the diagonal ones are called non-dimer pair. If one will try to solve the tight binding Hamiltonian, they will get this kind of band dispersion, where the points where conduction band and valence band are touching are called K points. And we can see about this point, the dispersion is parabolic. So the Fermi energy of bilayer graphene, pristine bilayer graphene will lie always nearly these K points. But this is the only reason which is accessible in the experimental limit, and these low energy bands are formed from non-dimer pair of orbitals. So I will be only talking about this low energy bands. So we understood that bilayer graphene has this low energy parabolic dispersion, and we know this bilayer graphene is a weak spin orbit coupling material. So if we put it on a single layer WSE2, which is a strong spin orbit coupling material, the band structure will get modified. So for this heterostructure, there will be an electric field which will be out of plane. And therefore, the two layers of this bilayer graphene will be at different potential. So the low energy band, which will be formed from the non-dimer orbital of the bottom layer, will be valence band, and the higher energy band, which will be formed from the non-dimer orbital of top layer, will be conduction band. Now, since the bottom layer is in direct contact with the WSE2, so it will feel a higher proximity, and there will be a large spin orbit coupling felt by that layer. So the valence band will be split. Now we can see the top layer is away from the WSE2, so there will be a weaker spin orbit coupling, and there will be a negligible splitting in conduction band. Now there is a proposal of spin orbit valve in this theoretical paper given by Dimitra and Fabian about this heterostructure, so which I am going to discuss now. So we understood for bilayer graphene and single layer WSE2, we will have this kind of band structure where valence band will be split because the bottom layer of bilayer graphene will experience higher spin orbit coupling as compared to the top layer. So if we apply an external electric field to the system, which will be in the same direction of intrinsic electric field, then the band gap for this dispersion will be enhanced. But if we are applying a field which is just opposite to the direction of intrinsic electric field, and it will be of the same strength, so now these two layers will be at same potential and the band gap will closes. If we are applying an electric field which is much larger than the intrinsic electric field, then in that case, the valence band will be formed from the non-dimer atomic orbital of top layer, and conduction band will form from non-dimer atomic orbital of bottom layer. So since the bottom layer is always in a direct contact with WSE2, so this time conduction band will show the splitting since it is forming from the atomic orbital of bottom layer. And there will be a weaker spin orbit coupling in top layer. So again, there will be negligible splitting in the valence band. So here we saw the band characteristic has switched. So this is what we have shown. We started from here, and by applying a external electric field, we got this band structure where the splitting has changed from valence band to conduction band. So this is actually very interesting problem. So let's say we have this kind of band structure where the Fermi energy is lying in the conduction band and it is in unsplit state. And if we keep the Fermi energy fixed and flip the direction of electric field, external electric field, we will get an unsplit band. So it can act like a switch where using the external electric field, we can switch on or off the spin orbit coupling in the system. There is also one more interesting thing, like if we can somehow keep the Fermi energy in between these two band edges, then we can do a transport, means spin filtered transport. So, okay, so now we will be discussing about our experimental results and observation. So this is our device heterostructure. where we have put a top gate and back gate. So the main purpose of having a top gate and back gate was that we can independently tune the charge carrier density and displacement field in our system. This is the device image without top gate, and this is after fabricating the top gate. Now first we measure a 4-probe resistance measurement as a function of top gate and back gate voltage. Then by using this formula, we converted the XY axis in carrier density and displacement field. So this is the plot where we can see for n equal to 0, there is a sharp bright color which is corresponding to higher resistance in this color map. So this is happening because of change in band gap as a function of displacement field, and this is one of the characteristic feature of bilayer graphene. Other than that, we also observed an asymmetric feature about n equal to 0. So let's understand this. So let's say we are in this region 3, where the displacement field is positive and our Fermi energy is lying in conduction band. So in this case, we should have a stronger spin orbit coupling in the conduction band, and that should be split. So instead of having a single bandage, we should have a double bandage, and that is what is reflected in the resistance plot. We also observed this for reason 2, where the valence band is showing the splitting. So there is a similar observation by another group where they have done the quantum capacitance measurement for the same kind of heterostructure, and they also find a asymmetric feature as a function of displacement field depending on the splitting in valence band and conduction band. So to further do a quantitative analysis, we did a low field magnetotransport measurement. We choose the constant number density line, this green line, and along this we performed the magnetoconductance measurement. So first we choose the quadrant 4, where there is no spin orbit coupling in the valence band, and we found that it is showing weak localization behavior. So this is what we expect in intrinsic bilayer, in a Preston bilayer graphene, because it also has a weak spin orbit coupling. And these red color curves are the fitting to this experimental data using theoretical equation. This is the parameter which we got after fitting. So the inter-valley scattering time was 0.9 picosecond, and phase decoherence time was 13 picosecond. Then we move to the reason 2, which is for a negative value of displacement field. Now this is the reason where the spin orbit coupling strength should be stronger as per this prediction, and this band should be split. So now when we did the magnetoconductance measurement here, we found it is showing weak anti-localization, and we did the fitting for this curve, which is shown by this red color plot. And the relevant time scale which we found, it was 9 picosecond phase coherence time, and the spin dependent time was 0.7 picosecond. So this is the highest spin scattering rate reported till now, which shows that there is a very strong spin orbit coupling in this system. So further, to probe the splitting, we performed a high magnetoconductance measurement. So we sit in region 3, which is the conduction band for positive value of D. We performed Suvnico-de Haas oscillation measurement, and we found there is a presence of beating, which says that there is 2 Fermi surfaces present in the conduction band. So that should look like this. So when we did a FFT for that, we found there are 2 frequency present, and that again says that there are 2 Fermi surfaces are present. Then we flipped the direction of electric field and again performed this measurement, and this time we found there is only single frequency when there is no splitting in the system. So this is also consistent with the theoretical.
Yeah, you have 2 minutes.
Yeah, I'm done. So this is also consistent with the theoretical prediction. So now I would like to summarize. So we selectively induce spin orbit coupling in the chosen band by using external applied electric field, and which was also reflected in the asymmetric feature in the resistance, which was function of displacement field, and that tells the presence of two band edges in the splitted band. Further, we did a low magnetotransport measurement, low field magnetotransport measurement, and there we saw transition from weak localization to weak anti-localization depending on applied external electric field. Later, we did a high field magnetotransport measurement to see the splitting in the Fermi surface in a high spin orbit coupling region. So this work I did under supervision of Professor Avik Breed and in collaboration of Saurabh Srivastav. Thanks. Now I'm open for questions and suggestions.
Yeah, thanks Priya for the very nice talk. So now the session is open for questions. So let's see if we have any question in the chat box. No. If somebody has question, please raise your hand. Okay. In the meantime, someone asked question. I have some question. So very interesting data. So I saw the beating effect. So what did you study the beating effect as a function of density? Like how does it depend on the gate voltage? You showed only one data, right? So one density.
Yes, I have shown only one data, but we have several data where we have seen the beating. But this is we have seen it at higher densities. Like this value is for n is equal to 3 and 10 power 16, but we do it for 2 in 10 power 16 also. But you cannot obviously do it for very low density because there will be.
I know, but do you still have the density dependence at this high density, and how does it vary? Because
okay, yes, I understood your point. So yes,
because if it is Rajba,
yes,
if it is Rajba, it should increase with the electric field, right? Spin orbit strength.
What I want to answer that depending on the number density, as you go in a higher number density, splitting is becoming more.
Splitting is becoming more. That's what you expect for Rajba.
Yes, and that is what has been seen in another paper also, but they have not done this field dependent measurement. So they did it single gate, and they also observed there is a dependence, this kind of dependence.
Okay.
Atin, I have a question. Shall I ask Chandni?
Yeah, Chandni, please ask.
Yeah. Hi, Priya. So in both the regions 3 and 2, you would see these beating patterns, is it? You showed one of the regions, but...
Yes. We should see the beating in region 2 also. Like if we go to the yes.
Yeah, so is this will this also give you some idea about what is the spin splitting here? I mean, the splitting of the band, because when you're somewhere in between the red and the blue, if your Fermi level is there, then you will not see this, right? No, could you get an idea of this?
We are in the band edge. So what I want to say, if we are exactly the number density of states will be very low. You cannot do this SDH oscillation there.
Okay, right, yeah.
Yes. So yes, but I have not calculated any splitting using this SDH oscillation. So
yeah, so you were way above the both the splits.
Yes.
Part. Okay. Okay. Yeah. Thank you.
So what was the mobility of your device, by the way?
So these are two different devices. The this weak localization data, it was of 25,000, and this SDS data, this was nearly 1 lakh.
1 lakh. So your Shubnikov DR starts from few hundred millitesla.
Yes.
Okay.
It was not. Okay. Maybe 200-300, nearly that. So it was.
Yes. Okay. Okay. So let's thank Priya again, and we'll move to the last talk of the session, and the last talk will be given by Purvasha Sarangi from NISER Bhubaneswar, and Purvasha will talk about observation of inverse spin Hall effect in COFI C60 interface. Yeah. So you can share your screen, Purvasha.
Okay, sir.
Do I have to unshare this?
Yeah, you have to.
I think it is already done.
Yeah.
Huh.
So Purvasha?
Yes, sir.
Yeah, it's okay.
Sir, is it visible?
Yeah, it's visible. You can do full screen. Yeah.
Okay, sir.
So you can start. Yeah.
Yeah. Okay.
Thanks.
Hello. Good evening. Good afternoon, everyone. So I'm
We cannot hear you. Can anybody hear?
No, can't hear her.
No, we can't hear you, Purvasha. Purvasha, are you there?
Maybe she's left and she's going to join again.
Yeah, maybe that's better. Maybe you can.
No.
You can disconnect and reconnect once more.
Hello.
Hello. Yeah, we can hear you now. Yeah.
Okay. Okay, sir.
Now please share your screen.
Yes, sir. Okay, sir. Is it visible?
Yeah, you can start now.
Okay, sir. So the title of my talk is Observation of Inverse Spin Hall Effect at Cobalt Iron Boron C60 Interface. So these are the outline of my talk. So first I will discuss about the motivation of this work. Then the experimental details, then result and discussion, and conclude with the summary. So usually for the spin pumping, high spin orbit coupling materials are used. So here but the organic semiconductor materials are the potential candidate because of their long spin diffusion length and the less hyperfine interaction, and also these materials are low cost material. But the problem of these materials are they have that spin orbit coupling strength is less for this material. However, it has been observed that due to the pi sigma hybridization at the curvature of the C60 molecules, it may increase the strength of the spin orbit coupling. So in this scientific report paper, they have observed the curvature enhanced spin orbit coupling and spin interface effect in the fullerene based spin valve. They have taken C60 and C70 molecules, both the spin polarized and the MEL data shown that the spin orbit coupling strength is more for C60. And it has also observed that the spin polarized charge transfer happened at the ferromagnet C60 interface. So in this paper, we have seen that when we are depositing C60 on top of a iron at the interface, the around 2 nanometer of C60 is getting magnetic, and it exhibits nearly 3 mu b per case magnetic moment. There is few reports on this spin pumping in ferromagnetic organic semiconductor. So here they have taken NiFe as a ferromagnet, and they have varying the organic semiconductor, like different organic semiconducting material they have taken, and they have used pulse ferromagnetic resonance to generate the ISHG signal. And they have observed for C60 film, it shows the higher ISHG signal in compared to the other organic semiconducting material. And the other paper is this, the Liu et al. They have also taken the NiFe C60 film, and they have also observed the spin pumping. Here they have taken the platinum layer that to detect the spin current. So our aim is to observe the spin pumping at cobalt iron boron C60 interface without having any heavy metal. So that taking the cobalt iron boron is the advantage of this. It's exhibit the low spin or low damping. And also we have observed the spin interface at a cobalt iron boron C60. So this is the experimental detail. So we have prepared 3 samples. So that is on top of silicon substrate, we have prepared single layer of a cobalt iron boron 10 nanometer, and cobalt iron boron we have deposited using DC sputtering. And then we have deposited the C60 having 4 nanometer and 20 nanometer. So this is the sputtering unit of our lab, and we have performed the FMR and ISHE measurement. So this is the FMR setup, and we have kept the sample in a flip chip manner on top of the waveguide, cool-planar waveguide, and basically we have made the contact at the 2 edges of the sample like this, and we have measuring the voltage using nano voltmeter. So observation of spin pumping and ISHE measurement were performed in the frequency range 6 to 17 gigahertz, and the angle dependent ISHE measurement at a we have performed at the fixed 7 gigahertz frequency. And basically for angle dependent measurement, we have rotated the sample like at 5-degree interval. And for the hysteresis loop measurement and the corresponding domain imaging, we have used measured using longitudinal MOC with plus minus 5 millitesla magnetic field. So these this hysteresis loop and corresponding domain images for all the 3 samples. So we have seen that the red curve is for 0 degree at the hysteresis loop at 0 degree, and this green curve is for hysteresis loop at 90 degree. So we have seen that hard axis is at 90 degree and the easy axis is at 0 degree, which tells that uniaxial anisotropy present in this system. And for all the system, this is same. So all the system exhibit uniaxial anisotropy. So we have seen there is a change in the HC in for all the samples. However, there is no change in the domain structure. So the change in HC may be the effect of the spin interface at the cobalt iron boron C60. To calculate the anisotropy of this system, we have performed angle-dependent ferromagnetic resonance. So this red curve is the single layer cobalt iron boron, and this blue is for that cobalt iron boron and C60 4 nanometer, and this green is for cobalt iron boron and C60 20 nanometer. So for this age resonance versus 5 plot, we have seen introducing a C60, there is that anisotropy is enhanced. We have also calculated the anisotropy constant for the samples, and that for cobalt iron boron 10 nanometer, the anisotropy is 2.97 into 10 to the power 4, and for cobalt iron boron C60 4 nanometer, it is 3.16 into 10 to the power 5, and for 20 nanometer C60, it is 5.04 into 10 to the power 4. So introducing a C60 layer, the anisotropy is enhanced, and also when we increase the thickness of the C60, that anisotropy is also enhanced. So this is the frequency dependent FMR FMR plot. So this is F versus H resonance, and this is delta H versus F. So we have plotted this plot. We have fitted these 2 plots, and from the fitting we have evaluated the damping constant, and we have seen for the cobalt iron boron 10 nanometer damping is like less 0.0085. However, when we introduce a C60 layer, the damping enhanced. So this enhance in the damping is also the indication of the spin pumping happening at the samples. So ISHE on the cobalt iron boron C60 samples. So here we have performed ISHE on cobalt iron boron C60 4 nanometer sample. This figure A is ISHE at 0 degree, and B is for the ISHE on 30 degree. This is ISHE at 90 degree, and this is ISHE at 180 degree. So this blue dotted uh, are for the experimental data of the VISH. Sorry. And this red one is for the fitted line. We have, so this ISH signal has both the symmetric and the antisymmetric component. We have decomposed the symmetric and the antisymmetric component. Here that red line is the symmetric component, whereas this green line is for the antisymmetric component. So we have seen at the 180 degree, the ISH signal get reversed, which is obvious because at the 180 degree, that magnetic field direction also reversed. And also at the 90 degree, there is less IHC signal. So at the 90 degree, we are measuring the voltage parallel to the applied DC field. So in this condition, the spin accumulation is less. So that's why there is less IHC signal. So this above two condition proves that there is a spin pumping happening at the cobalt iron boron C60 interface. So we have also measured the single layer cobalt iron boron spin like ISH measurement on the single layer cobalt iron boron sample, but for the single layer cobalt iron boron sample, we have not get any ISH signal. So this V like this V symmetric and V asymmetric, they have different like contributed.
Urvashi, you have 2 minutes.
Okay, sir. So this V symmetric part has contribution in the spin pumping and the anomalous Hall effect, and the V asymmetric part has contributed in the anisotropic magnetoresistance. So to calculate the V spin pumping voltage, we have measured the angle dependent FMR angle dependent ISH measurement. So this is V symmetry versus angle, and this is VA and antisymmetry versus angle for cobalt iron boron C60 4 nanometer, and this is for cobalt iron boron C60 20 nanometer. We have fitted the data using these two equations. From the fitting, we have get that the V spin pumping voltage for cobalt iron boron 10 C60 4 nanometer is 2.68 microvolt, and for C60 having 20 nanometer is minus 2.85 microvolt. So it has been observed that for that spin pumping voltage is more for the C60 thickness, like more for the sample 3, where the C60 thickness is also more. So in summary, we can tell that one can tune the magnetic anisotropy of this cobalt iron boron system introducing a C60 layer, and whereas there is no change in the domain structure. Damping also introducing a C60 layer, the damping also increases, and we have observed the spin Hall effect in the cobalt iron boron C60 system, whereas there is no ISH signal at the single layer cobalt iron boron. So, and that spin pumping voltage is more for having the C60 thickness is more. I want to thank my supervisor, Dr. Shubhankar Vedanto, and my co-worker, Dr. Brajbhushan Singh. So, and also the funding agency, DAE, DST, ACRB, all my lab members, and School of Physical Science, Niger. I want to thank the QMAT 2020 organizer for providing to give me the providing the facility to present this talk. So thank you all.
Okay. Thank you, Purvasha. So the session is open for now question. So if somebody has question, let me check in the chat box. Nobody is there. Okay. I have some technical question I can ask in between somebody.
Okay,
so the question is, you told that this molecule, you can deposit single layer. How do you make sure it's a single layer? You showed some data.
Sir, like C60.
C60.
No, sir, no, not a single layer. So single, whatever we have deposit C60, it is like single layer C60. One monolayer, it is 1.4 nanometer. So we have deposited 4 nanometer of C60. It is not like we cannot tell that it is a
You
monolayer.
cannot be sure
but
that.
But it is a continuous layer.
Yeah, but that then you cannot make sure that it's a single layer. Okay, and I think C60 is air sensitive, right?
Yes.
So then how did you take care of the oxidation of the C60 layer?
Yes, sir. So that whatever sample we have deposited without breaking the vacuum. And also like on top of C60, we have deposited 2 nanometer of MgO, which acts as a capping layer.
And do you think that MgO doesn't affect any property? Because sometimes if you use a capping layer, it can affect the properties of the whole system.
Yeah, but actually we have previously also we have we use capping layer like tantalum gold, and we have seen that for tantalum gold there is no change in the magnetic properties.
Yeah. Okay. Okay. So
maybe can I ask one question?
Yeah, sure.
Yes, sir.
Hi, nice talk. So how, I mean, do you have any understanding how this C60 is helping in the inverse spinol effect? Is there any? I mean, this inverse spinol effect that you are observing, I mean, in which way C60 is helping?
So in the usually this inverse spinol effect observed in the heavy metal, usually in the high spin orbit coupling material. So but in this organic material, the problem is they have exhibit low spin orbit coupling material. So in the previous report also we have seen the other organ like C60 is having more ISHG signal rather than the other organic semiconducting material, because C60 has like due to the pi sigma hybridization in the C60, so there is a curvature enhanced spin orbit coupling. So basically the spin orbit coupling is strength is more for C60.
So you mean in some way C60 is enhancing spin orbit coupling? Is that so? Or?
It might be the reason. And also in the ferromagnetic C60 case, so at the interface also, like interface also it is getting magnetic. So at the interface C60 getting magnetic. So maybe it also possibility that it may help in the spin pumping thing. But I'm not sure. Maybe this may be the reason.
Okay, thank you.
Okay.
Thank you.
So if there is no other question, okay, let's thank Purvasha again. And I think this was the last talk, and we'll end the session here. Okay, thank you all the speakers for this session, and thank you all for listening. Yeah.
Thank you.
Thank you.